In 2011, NASA's SWIFT satellite caught an X-ray outburst from a small galaxy 3.8 billion light-years away. Within a couple of days, researchers realized they were witnessing the aftermath of a tidal disruption event, a star ripped apart by the monster black hole at the galaxy's center. Some of the stellar material fell toward the black hole, forming an accretion disk and a jet pointed in our direction.
Tidal disruption events offer us this rare view at the most common kind of supermassive black hole in the universe, these so-called dormant supermassive black holes. 90% of black holes in the universe don't have a lot of hot material orbiting around them. They don't form these accretion disks, and so we can't observe them. Tidal disruption events, where the stellar debris causes the formation of a temporary accretion disk, offers us a way to probe this population of supermassive black holes.
SWIFT monitored the outburst's progress and was joined by the European Space Agency's XMM Newton Observatory and the Japanese Suzaku satellite. Recently, astronomers introduced a new analysis technique that for the first time allows them to peer deep into the gravitational well of a normally quiescent black hole. Called X-ray reverberation mapping, the method charts the region close to the black hole using light echoes from X-ray flashes, similar to the way sonar uses sound to map the ocean floor.
X-ray reverberation mapping has been very successful at probing the accretion flow in well-established accretion disk structures, but had never been used to look at tidal disruption events. My collaborator at the University of Maryland and I were having lunch one day, and she says, "Has anyone ever looked at tidal disruption events with X-ray reverberation mapping?" That night, I stayed late at the office and just tried it out on this data from SWIFT J1644, and much to my surprise, the result was amazing, and I could see that we were looking at the structure of the inner accretion flow around a normally dormant black hole for the first time. It's not like a normal accretion flow in an active galaxy that's a flat disk. This is something that is extremely puffy, very turbulent, and we are measuring flashes of X-ray emission deep within this newly formed accretion disk.
Stellar material streamed into the developing disk, churning it into a thick, chaotic whirlpool of X-ray emitting gas, funneling toward the central black hole. Deep inside this cavity, multiple X-ray flares erupted, providing a flash that echoed throughout the region.
Previously, astronomers had thought that the X-ray emission is coming from far out in a jet. But what we're finding with these observations is that the X-ray emission is coming from flares very close to the supermassive black hole. And we can use these observations to probe properties of the black hole itself. For instance, we found that the mass of the black hole is something on the order of 1 million times the mass of the Sun.
The first observations of X-ray reverberations from deep inside an accretion disk are providing new insights into a rarely observed class of black holes. They're also laying the groundwork for a better understanding of tidal disruption events and the black holes they illuminate.
Like a lot of kids, I grew up reading about neutrinos and people speculating about doing neutrino astronomy. And here I am, doing neutrino astronomy. I feel like I need to pinch myself. My name is Rupesh Ojha, and I'm an astronomer working at the Goddard Space Flight Center. I work with the Fermi Gamma Ray Space Telescope. What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. The Fermi Gamma Ray Space Telescope has an instrument called the Large Area Telescope, which we use to monitor the gamma ray sky, the highest energy electromagnetic band. And we just noticed that there was a tremendous increase in the amount of gamma ray light coming from this one extragalactic blazar. A blazar is an extremely powerful variable galaxy that is powered by a supermassive black hole. It went up not by a little bit, not by a few percent. It went up like 15 to 30 times its average flux. So we knew something was afoot. Later on, it turned out to be coincident both in time and in space with the neutrino that was detected by IceCube. IceCube is a neutrino telescope located at the South Pole, or to be more precise, under it. It consists of over 5,000 detectors that are spread out into a cube about 1 kilometer on each side. It's the world's biggest and its coolest telescope. So a neutrino is an incredibly small particle. It moves almost at the speed of light. It is nearly massless. It's incredibly plentiful, but it's very, very hard to detect because it will not interact with just about anything. If you could detect them though, because they have traveled through the universe essentially undeflected, they have information that you could not access in any other way. IceCube has detected a handful of extremely energetic neutrinos. One of them, which is called Big Bird, has an energy of about 2 peta-electron volts. To give you an idea of how much energy that is, it is about 1 million times the energy of a dental X-ray. IceCube sees too large a patch of sky to let us determine exactly which blazar Big Bird came from. The enormous increase in gamma ray flux seen by LAT and radio flux by other Tanami telescopes let us finger the exact blazar which is responsible for Big Bird. We have long suspected that blazars are the birthplaces of such neutrinos. What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. This is the first time that we can point and say that blazar is where this neutrino came from. Blazars are the brightest, steadily shining objects in the universe. However, many of the most basic questions about them, such as what is producing this tremendous amount of energy, remain open and unanswered. The same process that produces this neutrino could also produce gamma rays, and that would move us closer to an understanding of emission from near black holes in blazars.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows two neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the Sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
Parkes 1441 plus 25 is a distant galaxy powered by a supermassive black hole. It's so far away, its light takes more than half the current age of the universe to reach us. This is NASA's Fermi Gamma Ray Space Telescope, our sharpest satellite eyes on the gamma ray sky. But Fermi's effective collecting area is about the size of 2 office desks. It can't catch everything. Ground-based gamma ray observatories sport much larger light collectors than Fermi, but like traditional telescopes, they only work at night. Both MAGIC and Veritas work by catching faint flashes of visible light produced when a high-energy gamma ray strikes the upper atmosphere. This creates a shower of fast-moving charged particles that emit a glow called Cherenkov radiation. On April 16, 2015, Parkes 1441 was exhibiting high activity across all wavelengths. Scientists looking at Fermi data reported a strong gamma ray outburst. Based on this alert, scientists on the MAGIC team began monitoring the galaxy and detected very high-energy gamma rays. That was the cue for Veritas to take a look, and it also captured the quasar's very high-energy emission. These detections were remarkable because high-energy light usually can't travel extreme distances. These gamma rays had been traveling for half the age of the cosmos, passing through all the light emitted by stars, supernovae, and everything else that flashed and glowed across more than 7 billion years of cosmic history. Astronomers call this remnant glow the extragalactic background light. When a gamma ray strikes this lower energy light, it converts into a pair of particles, an electron and a positron. The farther gamma rays travel, the more likely it is they'll undergo this process, which effectively erases the gamma rays from the universe before we have the opportunity to detect them. Parkes 1441 is one of the most distant sources of gamma rays with energies above 100 GeV, tens of billions of times the energy in visible light. That the light reached us at all provides information about the extragalactic background light when the universe was half its present age. Those gamma rays originated from the particle jet produced by the galaxy's supermassive black hole. Astronomers think they started their journey only about 5 light-years from the black hole. Escaping the galaxy's crowded central regions means this high-energy light never interacted with matter or starlight, collisions that would have doomed them to convert into particles. This is one reason why extremely energetic gamma rays are few and far between, and why astronomers prize the relatively few photons they can find. The story of gamma rays from Parkes 1441 isn't a mere tale of survival. These photons executed a jailbreak of cosmic proportions, and it took Fermi, Magic, and Veritas to round them up.
Deep in the heart of the spiral Milky Way galaxy, a hot vortex of matter swirls around a black hole more than 1,000,000 times as massive as the Sun. Many galaxies, perhaps all, contain such a monster in the middle. These supermassive black holes sustain themselves by swallowing stars, planets, asteroids, comets, and clouds of gas that wander by the crowded galactic core. NASA's New Star spacecraft recently caught the Milky Way's central black hole in the act of having a snack. We got lucky and captured an outburst from the black hole during our first observing campaign, says Fiona Harrison, the mission's principal investigator at the California Institute of Technology. New Star is an orbiting observatory designed to take pictures of violent, high-energy phenomena in the universe. Launched on June 13, 2012, it is the only telescope capable of producing focused images of the highest energy X-rays, produced by the remains of exploded stars and ravenous black holes. It's like putting on a new pair of glasses and seeing aspects of the world around us clearly for the first time, says Harrison. New Star's sharp vision allowed it to pinpoint a burst of hard X-rays coming from the galactic center during an observing campaign in July. Lower energy X-ray observations by NASA's Chandra X-ray Observatory and infrared data from the Keck telescope in Hawaii confirmed the outburst. The Milky Way's black hole had just swallowed something. Black hole snacks are a violent process in which the meal is ripped apart by powerful tides, produced by their extreme gravity and heated to millions of degrees as they slide down the gullet of the gravitational singularity. In this case, New Star picked up X-rays emitted by matter being heated up to about 100 million degrees Celsius. The observation raises the hope that astronomers will be able to help solve a long-standing mystery. Why is the Milky Way's supermassive black hole such a picky eater? Compared to the giant black holes at the centers of other galaxies, the Milky Way is relatively quiet. More active black holes tend to gobble up matter in prodigious quantities. Ours, on the other hand, is thought only to nibble or not eat at all. Asteroids could be a primary food source. One model holds that trillions of asteroids surround the Milky Way's core. Astronomers using the Chandra X-ray Observatory have indeed detected flares consistent with asteroids 10 kilometers wide, or larger, falling into the black hole. These space rocks would be about the same size as the asteroid that wiped out the dinosaurs on Earth 65 million years ago. Smaller space rocks might be falling in too, but their flares would be too weak for Chandra to detect. New Star's capability to detect flares above the energy range explored in the past opens a whole new window on this problem and provides astronomers with a powerful new tool for understanding what's happening deep in the core of our galaxy. The monster's menu might soon be revealed.
Dark matter makes up about 27% of the cosmos, but so far no one knows what it is. Dark matter neither emits nor absorbs light, and it interacts with the rest of the universe primarily through gravity. In fact, it's thought dark matter traced the initial framework of the cosmos, attracting normal matter that formed stars and galaxies. Black holes are astronomical objects famed for their extreme gravity. Jeremy Schnittman, an astrophysicist at NASA's Goddard Space Flight Center, wondered if they could serve as a kind of laboratory for exploring different dark matter models.
The leading particle physics model for dark matter is called weakly interacting massive particles, or also known as WIMPs. These guys just fly through the universe without even bumping into anything or each other. The idea of two WIMPs coming together, annihilating and forming gamma rays is kind of like two bullets hitting head-on in a crossfire. It's very rare. But when you go to the area around a supermassive black hole, we expect the density to be much higher, so the probability of annihilation is much higher in this detection with a gamma ray telescope.
In Schnittman's computer simulation, a population of dark matter particles orbits a rapidly spinning black hole. Close in, at the brink of the black hole's event horizon, the particles are orbiting at nearly the speed of light. The lightly shaded region farther out is the ergosphere, a zone where all particles are forced to move in the same direction as the black hole's spin. The concentrated dark matter collides and makes gamma rays, but not all of this light can escape the ergosphere. The gamma rays most likely to make it out come from the left side, where the black hole spins toward us. The result is an asymmetric glow. The highest energy gamma rays come from the center of this region, corresponding to the black hole's equator. Schnittmann's work has uncovered previously overlooked orbits that can produce extremely energetic gamma rays, and has shown that the peak energy attainable for this escaping light is a strong function of the black hole's rotation. So far, the initial work is focusing on setting upper limits on dark matter annihilation rates by looking at otherwise quiescent galaxies, but Schnittmann's ultimate ambition is nothing short of an unambiguous detection of dark matter annihilation around supermassive black holes.
To me, dark matter, black holes, two of the most elusive things in the universe coming together to help explain each other is quite poetic.
For the first time ever, astronomers might have witnessed a star actually become a black hole right before our eyes, or telescopes. In this visible light image from the Hubble Space Telescope, we can see a large star about 25 times the mass of our Sun, around 22 million light-years away in the galaxy NGC 6946. This was in 2007, but in a Hubble image from 2015, looking with the same filters at the same wavelengths, the star appears to be gone. One possible explanation? The star died and became a black hole. But it gets weirder. The most prevalent theory for how a black hole forms is through a supernova. If a star is big enough, at the end of its life it will eject its outer layers at high velocity in a massive explosion, while the inner core collapses into a very tiny space, creating a gravity well so great that light can't escape. Literally a black hole. So did we see the star go supernova? No, not really. A team of astronomers was monitoring the star with a large binocular telescope in Arizona and saw the star get brighter in 2009, but not nearly as bright as a supernova. They call it a failed supernova. The star does expel its outermost layer, but relatively gently and not in a big explosion. Okay, so the star got brighter in visible light in 2009 and then disappeared in visible light. How do we know it's not just hidden behind a cloud of dust or something? The team checked for that. They looked at infrared observations from the Spitzer Space Telescope, which would be able to see the heat of dust warmed by the star. What we see with Spitzer is there is some emission in the mid-infrared, but it's fading and fainter than what you would expect to see with a hidden star. The team thinks instead that this infrared light is from the heat of gas falling back onto the newly formed black hole. To help confirm that the star is now a black hole, the team plans to analyze the observations taken with the Chandra X-ray Observatory, which would be able to reveal X-rays being emitted by the gas falling into the black hole. The team also wants to continue monitoring the star's location in visible light with Hubble, in case the star is still there and reappears. And they'll want to look at the location with the upcoming James Webb Space Telescope to check if there's a surviving star hidden by cooler dust than can be observed with Spitzer. So if this really is a black hole birth, what does that mean for astronomy? First of all, this would show that a star doesn't need to go supernova to form a black hole. Astronomers actually haven't seen as many supernovas occur with the largest stars as they would expect to see, and they've been wondering why this is. Perhaps 10 to 30% of massive stars don't go supernova, and they're still able to simply form a black hole. If future observations confirm this team's findings, this would be the first birth of a black hole ever witnessed and the first failed supernova ever discovered, both of which would usher in an exciting era of astronomy research.
A long-standing question in astrophysics is, how and when did supermassive black holes appear and grow in the early universe? New research using NASA's Chandra X-ray Observatory and the Sloan Digital Sky Survey, called the SDSS, suggests that an answer to this question lies with the intermittent way giant black holes may consume material in the first billion years after the Big Bang. Astronomers have determined the Big Bang occurred about 13.8 billion years ago and have evidence from the SDSS that supermassive black holes with masses of about 1 billion times that of the Sun existed by about 12.8 billion years ago. This implies that supermassive black holes grew rapidly in the first billion years after the Big Bang. Yet scientists have struggled to find signs of these growing giant black holes. To address this conundrum, an all-female team of researchers examined different theoretical models and tested them against optical data from the SDSS and X-ray data from Chandra. Their findings indicate that black hole feeding during this era may turn on abruptly and last for short periods of time, which means this growth may be difficult to spot. The timing of such growth may be key. The author's model suggests that 13 billion years ago, about 1/3 of supermassive black holes may have been accreting enough matter to be detectable. Just 200 million years earlier, a veritable blip in cosmic time, the number of potentially detectable black holes is only about 3%. In order to test this idea further, the researchers suggest that surveys with Chandra and future X-ray telescopes that look at larger areas of the sky in X-rays are necessary.